Okay, so let me begin. Uh, so the plan is to talk about why the fundamental theorem of Riemannian geometry works and try to develop a slightly better understanding of what goes behind it. Okay, so this is the title, Behind the Fundamental Theorem, and this is lecture 22. Right? So in case you have problems hearing me or there's some lag, just let me know and then I'll try to maybe go over that material once more. All right. So, okay. So we have seen a proof of the fundamental theorem. Recall that the fundamental theorem states that there is a unique torsion-free and metric compatible connection on a given Riemannian manifold M, G. So, so this is nice because in a sense it says that there is a canonical connection that you can obtain once you're given a Riemannian metric. Of course, there is the question of why are these two properties of torsion-free and metric compatible the right properties to look at, and that is the goal of these two lectures, to analyze why these two properties show up the way they do and what is the meaning behind these two properties. Okay. So remember, this unique connection is called the Levi-Civita connection, and the way we proved this in class was we proved this via the Koszul formula. What is the Koszul formula? Let me remind you that it was given by this identity. So it basically determines the connection implicitly by saying that the connection inner product any vector field Z is given by the right hand quantity, which has 6 terms involving Lie brackets inner product of the 3 vector fields X, Y, and Z. Okay. And then because the inner product is non-degenerate, you can actually solve for gradient XY or nabla XY because this is true for all Z. So that was how we determined nabla XY, and then we showed last time that this is smooth, it's a connection. So this is one way of implicitly defining a connection using the inner product. And then it turns out that this is something which is metric compatible, it is torsion free, and anything which is metric compatible and torsion free has to be of this form, so it's unique. Okay, so let's analyze the two key properties, so which are stated here: metric compatible, torsion free. Right. So a connection is called metric compatible if the following identity holds. So this is for all any pair of any triple of vector fields, sorry, X, Y, and Z. So it says that if you take the inner product of Y with Z, that's a function. You direction differentiate the function along the vector field X, that should be the sum of these two terms. So this is almost like a Leibniz rule in a sense, right? So we'll see what this means, but this is what metric compatibility is defined to be. Okay. So as is usual in such a scenario, you work in a local chart and try to gain some information regarding what this says about the metric and the Christoffel symbols. Remember that connection is determined in local coordinates through its Christoffel symbols, and a metric itself will have its own Christoffel symbols because a metric determines its geodesics. And these two are usually not the same unless the connection is the Levi-Civita connection. So nonetheless, so you should work locally in a chart u comma phi, and the coordinates are x1 through xn. Okay. So the obvious thing to do at this point would be to choose local vector fields on u, which is of the form d by dxi, d by dxj, and d by dxk. So you set x to be del I. So del I is going to be my shorthand for today for del by del xi. Same with y, it is del by del xj, and same with z, it is del by del xk. Okay? We're going to plug in these three things because any vector field on u is going to be a function linear combinations of these del by del xi. So it suffices to check what this metric compatibility identity here gives me for these three vector fields, right? Okay. So if we move on to the next slide. Okay. Just a second. Okay, so we calculate. So you look at this quantity, the first quantity that appeared on the left. So this is going to be nothing but the inner product of the vector field del by del j with del by del xk. but this is by definition the quantity GJK, right? The Riemannian metric in local coordinates, GJK is the inner product of del by del J with del by del K. And this d by del I simply becomes the partial derivative of the jkth coordinate of the Riemannian metric in the xi direction. So that's all. This is just a notation. But we're going to introduce this notation, which I had also introduced in class once, I think, that this is a shorthand. Instead of writing all of this, we'll write gjk comma I. So gjk comma I is going to stand for the ith partial derivative of the jkth entry of the Riemannian metric. So the Riemannian metric in local coordinate now is basically an actual positive definite symmetric invertible matrix at every point, and the jkth entry of that matrix at the point P is inner product del by del xj del by del xk at the point P. Okay, so this is our notation. So what about the next term? Well, the next term you simply have to plug in. So what is nabla xy? This is going to be the usual thing with Christoffel symbols, right? So x is del by del xi, y is del by del xj. So in Christoffel symbols, this is going to be gamma superscript L, ij del by del xl. Okay, so these gammas are the Christoffel symbols of the connection. They have nothing to do with the metric so far. And then inner product with del by del k, because that's what z is. Now, if you take the inner product, what will happen? Well, these two will contribute a GLK. So that's what you get, right? It's gamma Lij GLK. But I'm going to also start using the Einstein summation convention, which means whenever I have this sum, the only thing that's being summed over is L. But it's also evident in the notation that L appears at the top as well as in the bottom. So whenever I write an identity or a symbol like this, this means that this is a sum over all those indices which appear at the top as well as at the top and at the bottom. So this means this is a sum over L. So, and I'll be using it to save space as well as it's easier for me to format various equations because I'm giving a lecture on the slides. So I hope this is clear. So keep in mind that this is a sum. This is not one single term. This is one single term. There's no sum. All right. So let's do the next one. The next one is y. Well, y was del j or del by del j. What is this? This is going to be nabla del by del xi del by del xk. So this is going to be the gamma superscript L ik del L. But then you expand in the same way, and what you get is this. But again, this is a sum, okay? Because L appears on the top as well as at the bottom. So if the metric compatibility condition says what? It says this term is the sum of these two, which means this quantity has to be the sum of these two quantities, but these themselves are sums, right? Okay, so written this way, this doesn't quite reveal much. It's just saying that you have some equality between certain derivatives of the Riemannian metric and the Riemannian metric combined with the Christoffel symbols of the connection. Okay, fine. So we'll have to extract something more out of this. So here's an exercise. See, one of the curiosity questions at this point would be that how are the Christoffel symbols of the connection related to the Christoffel symbols of the Riemannian metric? Remember, in the solution of geodesic associated to a Riemannian metric, the Christoffel symbols were all partials with respect to the metric and then the inverse of that. So this is what leads to this exercise, that you can show with the fact that this quantity is the sum of these two, that this equality holds. Okay, so this is a half in front, but you're summing two things, the ith derivative of gjm and the jth derivative of gim, and you're subtracting the mth derivative of gij. And if you do that, you're going to get three terms on the right. And again, here this is a sum because the L appears on the top and the bottom. This is also a sum. This is also a sum. So these three terms are all sums over L, right? So use the metric compatibility identity to show that this is what happens. And the reason I'm pointing this out and assigning you as an exercise is that remember that this quantity, this left-hand side, when you multiply it with G upper Km, so the Kmth entry of the inverse of the Riemannian metric, and if you sum over M, then that became the Christoffel symbol associated to the Riemannian metric. So one would like to basically get hold of the Riemannian metric associated to, I mean, the Christoffel symbols associated to G, and compare it with the Christoffel symbols that you get for nabla, because nabla is not necessarily the Levi-Civita connection. That's the reason why I'm assigning you this exercise. Okay, but more importantly, what you note is the following: that the right-hand side has three very specific looking terms. So this one would be tempted to call the symmetric version of the Christoffel symbols, or the symmetrization of the connection, because gamma Lij need not be equal to gamma Lji in local coordinates. But if you treat it this way, then this is inherently symmetric in I and j, right? This term. So you can think of this as symmetrizing the Christoffel symbol associated to a connection. What about this term? Well, this is skew-symmetric, right? Because if I switch I and m, I get a minus sign. So this is the skew-symmetrization of the Christoffel symbols of the connection, and this is also a skew-symmetrization. Okay. However, the total thing is symmetric, because if you switch I and j, these two terms entirely switch. But individually, this is a skew-symmetrization, this is a skew-symmetrization, and this is a symmetrization. Because gamma Lij need not be gamma Lij, neither is gamma Lij equal to minus gamma Lji. Okay. So are there any questions so far? I'll just pause here for a moment and see if people have questions. Okay, all right then. So let's move on. So yeah, so this is what I just said. The right hand side contains symmetrized and anti-symmetrized Christoffel symbols. So we'll just add a notation, and I'm not sure what is the standard notation for this. So I'm just going to use this. So this is symmetrized, S for symmetrized. Lth superscript Lijth Christoffel symbol is simply going to be half of this. Okay? And of course, if the Christoffel symbols were symmetric in I and j, this is simply going to be gamma Lij, right? Similarly, the anti-symmetrized one is this. And obviously, if the Christoffel symbols were anti-symmetric, then A Lij is going to be gamma Lij. Okay, so here is an exercise, and this is almost immediate now, that if the Christoffel symbols are symmetric, then show that the Christoffel symbols of a metric, of a connection which is metric compatible, and the Christoffel symbols of the Riemannian metric G are the same. Okay. So why is that? So if the Christoffel symbols are symmetric, that means what? That means the anti-symmetrized Christoffel symbols are zero. That's what saying something is symmetric means. Which means this quantity is zero, which means gamma Lij is equal to gamma Lji, which means it's symmetric in I and j, right? So now if we go back to this equation, this term vanishes because you're switching I and m. This is zero, this is zero. So what you're left with is exactly this term, right? But what is this? This is now gamma Lij, because gamma L is symmetric in I and j. So this is simply gamma Lij GLM. But now if you recall how we obtained the Christoffel symbols from the geodesic equation, this is precisely what we did. So that's just one step away from the claim that the Christoffel symbols of the connection is going to be the same as the Christoffel symbols that you get for the Riemannian metric in order to define the geodesic equation. Okay. So it's just that these two terms drop off, and this simply becomes gamma Lij. Okay. So I'll just leave it to you to check this, but secretly all I'm assigning you here is another variant of the Levi-Civita connection, or the uniqueness theorem, fundamental theorem of Riemannian geometry, to go back and think about it. Okay, so but this is, I'm just give it a try, and then we can discuss this if you are stuck. Okay. So I want to go on to the next property, which is torsion free. So a connection is called torsion free if this quantity T nabla, which is called the torsion, is zero for any two vector fields x and y on M. So this is a nice algebraic quantity. It's a bit mysterious as a geometric quantity, and our aim would be to at least shed some light on what is the real meaning and geometry behind this quantity called torsion, okay, which is usually not present in most of the modern textbooks to my liking. But if you read some of the old masters, then this is how it was motivated and defined. But nonetheless, this is a very nice algebraic quantity for one reason. it is nice because it's a tensor, and this is something we checked. Okay, so it's a tensor, so it makes sense to say that this is, I want this to be 0, for example. Okay, so let's see what this is in terms of the Christoffel symbols expressed in a local in local coordinates. Okay, so let's see. So in local coordinates, again, you take x to be del by del xi, y to be del by del xj, and you write down the torsion. Well, it's going to be this, remember, because the Lie bracket of del I and del j are going to be 0, because these are the usual grid coordinates, and the d by dxi is the flows, commute with the flows associated with d by dxj's. So that's why there's no Lie bracket. The only terms that you get are the Christoffel symbols appearing in precisely this way. This is ij and this is ji. So if you simplify, what happens? So if you pull out the del k, what is this? This is gamma k ij minus gamma k ji. But that is precisely 2 times the antisymmetrized Christoffel symbols, which is what we introduced in the last slide, right? Okay, so if you say that your torsion is 0, that means it suffices to say that the torsion is 0 for any choice of I and j, because it's a tensor. You can take linear combinations here and multiply by functions. This is still going to be 0 once it's 0 on a basis. Okay. So this being 0 for all I and j means that this quantity twice the antisymmetrized Christoffel symbols are 0, because del by del x k forms a basis. But that simply means what? That simply means gamma k ij equals gamma k ji, right? So, I mean, this is 0, so only 2 terms. So that's what. A connection is torsion free if and only if the antisymmetric part vanishes identically, which means gamma k ij is gamma k ji for all k and I and j. But this was also introduced in the class, or at least I made a remark saying that often one calls a torsion-free connection symmetric, and this is the reason for it. Okay, because the connection, the Christoffel symbols do not have any antisymmetric part; they are symmetric. Okay, but that's equivalent to saying that the torsion is 0. So, any questions or comments so far regarding what we have deduced? All right. So here is another exercise, and again, this is all exercises connecting and associated to the fundamental theorem of Riemannian geometry. So it says, show that the geodesics of a torsion-free metric compatible connection coincide with that of a metric. So remember, how do you define the geodesic of a connection nabla? A geodesic of a connection is defined to be a curve gamma, which satisfies nabla gamma dot is 0. Right? And this is simply motivated by the fact that for the Levi-Civita connection, a geodesic on M is precisely a curve which satisfies nabla gamma dot is 0. But then you can say that, okay, I don't want Levi-Civita connection. You can forget about the metric, and you can just say for a connection having nothing to do with the metric, a geodesic is simply a curve which satisfies the same equation as before. Nabla gamma dot with respect to gamma dot is 0. So the question here says that if your connection is torsion free and metric compatible, then the geodesics of the connection and the geodesics of the Riemannian metric are the same. So let me just say one line, and then for those who have been following so far, you can probably see why this is true. See, torsion free says that the connection is symmetric, which means the antisymmetric part is 0. Metric compatible means you have that the very first identity that we had. The k derivative of gij is equal to something to do with the Christoffel symbols of the connection. But that had 3 terms on the right hand side, and 2 terms will drop off because the connection is symmetric. And the only term left is going to become gamma kij of the connection. But you can deduce from that the Christoffel symbols of the connection and the Christoffel symbols of the metric becomes the same in this case. Whence the geodesics are also the same, because they determine the geodesics in both cases. So in effect, this is also saying that if you have a connection which is torsion free and metric compatible, then the geodesics of the connection is the same as the geodesics of the original manifold. But this is in in circumspect, this is basically the Levi-Civita connection. So we know that already, but this is just a way of warming up to whatever we're going to say now. Okay. So yeah, anyway, so the point is the usual geodesic equation looks like this, right? It's d2xk over dt2 plus there's this Christoffel symbol, and just pay attention to this. I am writing gamma of g as opposed to gamma kij because this is supposed to be the Christoffel symbols for the Riemannian metric g. So remember, this can be determined in terms of the partial derivatives of the metric, and then you have to invert the metric. Okay, so this is what that quantity is, and then you have dxi dt, dxj dt. Okay, so this is how you solve for the geodesic equation for a Riemannian metric, and it's pretty clear that this quantity, as we had defined much earlier, is symmetric in I and j. There's nothing to check there. Okay. So the exercise here basically says that if you look at the usual gamma kij from up here for a connection with these two properties, that gamma kij should equal this gamma g kij, and everything else follows. Okay. Okay. So any questions? Otherwise, I'll maybe move on. Okay. All right then. So let us consider geodesic defined by a connection, and this is something I alluded to maybe a few minutes back. So this is what? This is basically a curve gamma satisfying this equation, right? Okay. So let's write it down in local coordinates. So gamma looks like x1 of t up to xn of t, right? So what should this quantity be? Nabla gamma prime is nabla dxi dt del by del xi, dxj dt del by del xi. Remember, this is not one single term. This is a summation because I'm using the Einstein summation convention here. Okay. So this is simply what you get by differentiating gamma with respect to t. This is just the chain rule. Okay. So this is a sum over I, this is a sum over j. I hope that is clear. Okay. So now what do you do? Well, you know that this is C infinity M linear in the subscript slot. So these dxi's can come out, and this is satisfies the Leibniz rule in the top slot. So there will be two things that come out, right? So let's do the first one. So these dxi dt's come out because it's C infinity M linear in the superscript, I mean in the subscript, right? Now here you have to apply the Leibniz rule, right? Which means either the dxj dt will come out and you have nabla del I del j, or you have del by del xi of dxj dt, and then you have the usual del j. Okay. So this is what you get. Okay, I'll just pause for a moment. You can have a look and convince yourself that this is exactly what you get by applying the Leibniz rule to where the connection is acting on. All right. Okay. So what do you get here? Well, this quantity simply becomes this. It's gamma k ij, and there's a del by del k. And this quantity, remember, this is simply going to be just the second derivative of xk because you're doing del by del xi dxi dt of dxk dt, but this is just the chain rule. So this will simply give you del 2 xk by dt2 del k. Okay. So that's it. So I just pull out the del k outside, and what I get is this quantity. Right? All right. So yes, and you have to remind yourselves that this is a sum here. Okay, this is one single quantity. The sum k is happening at the very end, but this is the coefficient of del k, and this term here is a sum. It's a double sum over I and j because I appears up and down, j appears up and down. Okay? And that is expected because that is what we also see in a geodesic equation. Right? Okay. So what do these geodesics associated to a connection must satisfy? These must satisfy this equation, right? d2xk dt2 plus these terms, but here I'm just combining I less than or equal to j because remember here this is a double sum, but dxi dt, dxj dt they commute because I'm looking for smooth solutions. But dxi dt, dxj dt they're simply functions. As long as they're C1, for example, or C2, they commute. So that's why I'll be replacing the sum instead of for all I and j with I less than or equal to j. and now I'm only counting terms of the form dxi dt dxa dt once, and the coefficient now becomes a sum. Okay? And it's inherently symmetric, the sum, simply because it's symmetric in I and J, because I symmetrized it by using the sum. Okay. 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 So just a second. So yeah, so the upshot is the following: that if you wanted to calculate a geodesic for a connection, it's determined by the symmetric part of the connection. That's the upshot. That the antisymmetric part never appears in the geodesic equation for a connection. Okay. So this,
Sir, sir,
yes.
in the previous thing,
Here,
sir, if I equal to J, wouldn't we have a 2 there?
I is equal to j, then you have two. Uh,
2, but
okay, yes. So I guess right, you're right. So there's a small typo. So I guess the best thing would be to divide by two here, okay, and then let this be all I and j. Okay, I think that's the best way. So instead of the sum being reduced from all I here, I reduce the sum, but just ignore this part. Okay, keep it the usual sum, all I and all j, but make this gamma k ij plus gamma k ji divided by two. And that works because whenever you're taking the ij term, it's going to be gamma k ij plus gamma k ji, and you'll be looking at the ji term. And when you add them both up, you're going to get back the old sum because these two things commute. And for I equal to j part, you'll get gamma k ii plus gamma k ii by 2, which is just gamma k ii, and there's only one such term. Okay. I think that's so. I really wanted to divide by 2 and then put skij here, but I probably should have done that. I think that works, and the summation is over all I and j. Does that help?
yes, sir.
Yeah, so it's so ideally this is the symmetrized version skij, and this is the same old sum, no I less than or equal to j. So the point at the end being whatever these coefficients are, that the geodesic equation only requires the symmetric part of the tensor. It doesn't require or see the antisymmetric part. Okay, that's the point. Yeah. So just make the appropriate change here. Divide by 2 and just ignore this part. Any other questions? Okay. So yeah, thanks for this pointing this out. I'll fix this. So yeah, so the upshot is that the geodesic associated to a connection nabla is determined by the symmetric part. Okay. Now, what determines the antisymmetric part? Well, you saw that torsion, when you calculate, is exactly the antisymmetric part, right? It's 2 times the antisymmetric part. So the torsion is capturing the antisymmetric part. Geodesics for a connection is capturing, or at least in some senses related quite intimately to the symmetric part of the connection. And if you have an object and you know the symmetric part and the antisymmetric part, then you know the whole thing. Correct? So here's one small exercise, and this is almost immediate at this point. But again, these exercises are exercises for you to go back and do, and these are official exercises. In case I do not get the time to gather all of them in one single PDF, we have to basically look through the slides, and wherever a red line shows up without an asterisk, that's an usual exercise. Okay? So anyway, show that two connections have the same geodesics if and only if the symmetrizations are the same. But at this point, it's almost evident that that is true because the symmetrizations are the only ones determining the geodesics. Okay. Okay. So if you want to deal with tensors and you like those kind of things, then you can rephrase the exercise as saying that if two connections have the same geodesic, then the difference is a tensor and it's an alternating tensor. Okay. Anyway, so it's the same thing. So since we have seen that torsion captures the antisymmetric part and geodesics of a connection sort of captures the symmetric part, we have this theorem, and this theorem is not as hard based on how we develop things. Okay, in fact, I would argue that this theorem is much easier than how one proves the fundamental theorem of Riemannian geometry, which almost comes as a magical thing using the causal formula that it seems to work out. without no clue why it happened. But if you argue this way, it's pretty clear. You have this theorem. This says that two connections with the same geodesics and torsion are equal. Okay, so I hope the proof is now evident as to why they are, because one controls the antisymmetric part, the other controls the symmetric part, and the two together put together gives you the connection, at least locally. But everything is local anyway. We work in a local coordinate with Christoffel symbols. So that's it. So this is a very nice theorem uh, which tells you when two connections are equal. Okay. So of course you might object to this, saying that okay, torsion is something we can really compute, but what about all geodesics? Well, all geodesics is not something you can practically compute, but this is an abstract theorem anyway, which helps you characterize things. So it's nice to have such theorems as well. So there's an immediate corollary of all of this discussion. So the corollary is that there is at most one connection which is torsion free and metric compatible. Right? That's immediate, because you cannot have two connections which are not the same but they're torsion free. That means the torsion is the zero tensor. And metric compatible and torsion free, remember we concluded, means that the geodesics of such a connection is the same as the geodesics of the Riemannian metric. So two such connections will have the same geodesics, have zero torsion, but they cannot be such because of the theorem. So there's at most one. So I'll just pause here for a moment and I'll let people just read it on your own and see if you have any questions regarding whatever we discussed so far. Okay. All right. So the corollary is almost close. Yes.
Sir, I get that if two connection, if a connection is torsion, if two connections are torsion free, then both of their torsions are equal. Now, how does the metric? Can you repeat? How does the metric compatibility come into play?
Sure. So I'm saying, see, torsion free means you're saying that the torsion is zero, right?
Yeah.
So you have to prescribe to me all the geodesics and the torsion, and then the theorem says there's a unique connection with that data, correct? So torsion free means I'm prescribing the torsion to be zero. Okay. Now, if you go back go back to the first few slides where we discussed that if you have a torsion free and metric compatible connection, then one of the exercises which will be immediate is that the geodesics of such a connection is nothing but the geodesics of the metric. But the metric is something you have already to begin with. You were starting with the Riemannian manifold M comma G, right? So the metric itself has its own geodesics, which comes from this equation d2 xk over dt2 plus the Christoffel symbols of the Riemannian metric times dxi dt, dxj dt. The sum is equal to 0 for all k, right?
Yeah.
So the Riemannian metric itself has its own geodesics. It does not need a connection, so to speak. So now when you look at a connection which is torsion free and metric compatible, then we discussed, and I left the last bit as an exercise, that for such a connection, the geodesics of this connection will be nothing but the geodesics of the Riemannian metric. But the Riemannian metric is a choice that you start off with, which means that the geodesics for such a connection is nothing but the geodesics of the Riemannian metric, which is fixed. So you are prescribing. So in essence, you are prescribing zero torsion, and you're saying that the geodesics of this connection are nothing but the geodesics of the Riemannian metric. Then the theorem says that there is only one such connection with this data. Okay.
Yeah.
Are there any other questions? Okay. All right. So we are very close to the fundamental theorem. So this is an at most one kind of statement. So to prove the fundamental theorem along these lines, we have to show that there is at least one connection which is torsion free and metric compatible, and then we'll be done, because this says there's at most one, right? So since we have already discussed the existence of one such connection via the Koszul formula, for instance, at the very beginning of the slides we said that. So the corollary also implies the fundamental theorem. Okay. So, I mean, what I want to point out categorically here is that the corollary is not the important point of this discussion. The important point was this uniqueness theorem, which says that you have to really understand geodesics and torsion in order to determine a connection. This is really going on at the heart of the fundamental theorem, not the specific fundamental theorem. So in a sense, the fundamental theorem is a very special theorem out of all theorems, which this general theorem of uniqueness is. Okay. So yeah. So anyway, so the point is, if you're given uh, the Christoffel symbols obtained from a metric, you can always write down the Levi-Civita connection. So that is another way of defining the Levi-Civita connection without using the Koszul formula. So how do you do that? Well, you declare the Christoffel symbols for your connection to be the Christoffel symbols of the metric. So declare gamma Kij to be gamma G of Kij in some chart. But then you have to put them all together to define a global connection. How do you do that? Well, you have to patch them up, and you have to know the transformation rule for the Christoffel symbols, right? And this is something I had assigned as an exercise, I think, quite a while back, and I don't know how many of you went back and did it. Probably very few, but if you haven't, this is as good a time to just get a couple of, like sheets of paper, sit down and just prove it that the Christoffel symbols will satisfy this transformation rule. Okay? So it looks complicated if you were to determine this on your own, but since you're given what the rule is, it's now a matter of just checking. Sit down, okay, maybe with a cup of tea or whatever, relax, and then write down all these things and check that the Christoffel symbols satisfy this property. Okay? And once the Christoffel symbols satisfy these properties, you can show that Christoffel symbols defined on local coordinates can be patched together to determine a global connection. Okay? So this is the transformation rule of how Christoffel symbols change if you change coordinates. Right? So I'll not say much about this because this was assigned much earlier, and you should just check it. Okay. So the point is, we had said that you have to use this to prove that the geodesic equation is well defined, because the geodesic equation is defined in terms of local coordinates. And how do you know that the equation is well posed? If I change the coordinates, maybe the equation changes structure, and this is what we used to show that. And it was half a board calculation that we did in the class. So this equation appears again, this identity. Okay? So the point being that you can define the Levi-Civita connection without using the Koszul formula by declaring the Christoffel symbols of the connection to be the Christoffel symbols of the metric, and then checking that this is the transformation rule. Okay. All right. So this is a more analytic way of defining the Levi-Civita connection, and some of you might like it, those who like computations. So okay, so that takes care of the title of the lecture. So this is what I meant by behind the fundamental theorem. So let me now move on to what metric compatibility really means, and let me begin to talk about what or how one should interpret torsion and what torsion free means. Okay. So if there are no questions, allow me to move on. Okay. So the first thing I would like to briefly review is the notion of parallel transport, and this is going to be a very short review. So remember that if you're given a connection nabla and you're given a smooth curve, so I is going to stand for, let's say, any compact interval, AB or 0, 1, and a vector field X defined along gamma. So the vector field is not going to be necessarily a global vector field, but X is going to be a smooth vector field along gamma, which means for every point gamma t, I have a vector X of gamma t, which is a tangent vector at gamma t. That's what a vector field X is. So you declare this vector field to be parallel if this quantity is 0. Okay, so this is 0 for all t. So just one point to note is that this quantity itself does not quite make sense the way we have defined a connection. In order to evaluate a connection, we need a vector field and we need a vector field. But what we had deduced in class was that the connection is a local property. So you have to basically know this at a point and know this around that point, basically. Okay. So what you do is, given this x along gamma, you simply extend x to a neighborhood of gamma, a neighborhood of the image of gamma by a partition of unity, for example, yeah, if you want. So then you can make sense of this identity equal to 0, and it turns out that that is independent of the choice of x. So this is something we had discussed at length in class, but that is what this means. Okay, just because you have a vector and you have a vector, it doesn't mean nabla of a vector and a vector makes sense. You have to extend them to at least local vector fields, and only then can you talk about the covariant derivative. But I'm assuming you have done all of that here. Okay. So this is an exercise which I had maybe orally assigned in class, but I'll assign it officially now. So this is again an application of Picard-Lindelof theorem, that if you're given a curve with the initial tangent vector at gamma 0, show that there is a unique parallel vector field x such that x of 0 is v, which means x is going to be a vector field satisfying this equation defined along gamma, and x at time 0 is the initial vector that you have prescribed. Okay, so such parallel vector fields exist. That's the point. This is pretty much like an integral curve. I mean, like the solution to the existence of integral curves, you have to use some version of Picard-Lindelof. Okay, so why am I recalling this? Well, remember the metric compatibility condition looks like this, right? Okay, so let's take x to be gamma dot or gamma prime. So x is now going to be a vector field, which is simply the velocity vector field of a curve gamma, right? Okay, and I take y and z to be parallel to the curve. So I do not take any arbitrary vector field y and z. I choose my y to be parallel to gamma prime, and the same with z. What does that mean? Well, that simply means that this term over here is 0, correct? Because y is parallel to x and x is gamma prime. Similarly, this term here is 0. So what do I get? I basically get that the directional derivative of the inner product y with z in the direction of x is 0 plus 0, which is 0. But what is x? X is gamma prime, and directional derivative along gamma prime simply means you're differentiating along the curve gamma. Okay. So that's what we're going to write down next. So with this specific choice, these two right-hand side terms become 0. So what we observe? Well, we observe that the left-hand side has to vanish identically as well. But the left-hand side is nothing but the dot product of yt with zt, and you are differentiating along gamma prime. But that simply means you have these two vectors y and z along the curve gamma. You're taking the dot product, and then you're saying this dot product is a constant along gamma because its derivative is 0, right? So in particular, it says two things. It says that if z was equal to y, then it's saying that the z of t has constant length as you move along gamma, right? Because you're saying that the d by dt of inner product zt with zt is 0, but that means zt with zt itself, that's the length square of z, is a constant as it moves along gamma. And in particular, because the lengths are preserved of parallel vector fields, the angles are also preserved by the cosine law. So in particular, if you take two parallel vector fields, and so if you take two parallel vector fields, the lengths and angles between them are preserved along the curve gamma for which they are parallel vector fields. Okay. So is this clear? What this, so this metric compatibility in this specific setting gives me that. It says that if I take two vectors, I parallel transport them along a curve, the lengths and the angles between the vectors are preserved. That's another way of saying it. Okay. So in a sense, it's saying that if you think of the metric at a point, the metric at a point is determined by lengths of vectors and angles between vectors. So if you want to see how the metric changes, you simply choose a curve and then you take two vectors, parallel transport along the curve, and this is in a sense saying that the metric is unchanged along all curves, okay, so to speak. So yeah, that's what you just said. Okay, so we'll talk about a slightly different way of talking about metric compatibility in a moment. But before I do that, are there any questions or remarks about this first aspect of metric compatibility? Okay.
Sir, can you give a pictorial view of what does parallel field means? Like the definition which you gave was the mathematical definition, but how can we pictorially visualize that?
So see that there's no, okay, so the answer to your question is there's no concrete pictorial description, simply because a random connection is just a very random thing. So if I give you a connection, a parallel vector to the connection is simply going to be something which satisfies that equation. Okay? Because you have to see, the only connection that you can sort of draw or say is nice is the one which is compatible with the metric or something of that sort, or maybe I misspoke. So something which is usually the Levi-Civita connection. Okay, but the point is, in the case of the Levi-Civita connection, when you say something is parallel, the only example that you can immediately think of is that of a geodesic. So a geodesic is saying that if you take gamma to be a geodesic of the connection, let's say, then what happens? Then you basically, so you can sort of, let me go back one step here. So in here, if you plug in x to be equal to y to be equal to z to be equal to gamma prime, okay, and let's say gamma prime is a geodesic for the connection nabla. So what would that mean? That would mean that nabla gamma prime is 0, but that would mean that this is 0 and this term is 0, right? Which would mean that the right hand side is 0. But then if you didn't have metric compatibility, then that's the end of the story. I mean, a geodesic with respect to a connection is just an arbitrary thing. It has nothing to do with the metric. So there is no inherent picture that you can draw. If it is metric compatible, then it turns out that you start with a geodesic for the connection. So nabla gamma dot is 0. So this term is 0. Same happens here. And because of this identity, what you get is the dot product of gamma dot with gamma dot, which is just the speed square. When you differentiate along gamma dot is 0. But that simply means that the speed is a constant of such a curve, right? So in particular, if it's metric compatible, you're seeing that a geodesic of associated to a connection will have constant speed. But this is still not a geodesic associated to a metric. But that's a different thing altogether. And a geodesic associated to a metric also has constant speed. But this is at least getting closer to that. In the sense, it's saying that a geodesic associated to a connection will have constant speed. So it looks more and more like the geodesic of a metric. Okay? But you still have to do a lot more work. It will still not be a geodesic because of torsion. And to answer your question, in general, if you say x is parallel to, so this is just something that you have to solve. So in other words, you have to say that if I have okay, so let me, so there is a picture for your question, but the picture is again going to be very specific. So so before I say that, I mean, was this explanation clear up to this point?
Yes.
So now if you want a more precise explanation, what you could do is you could say, okay, let me take x to be gamma dot and y to be gamma dot. Okay, fine. And I choose my gamma dot to be a geodesic for nabla. So far I'm not talking about geodesics for the metric. So just keep that in mind. I'm repeating myself, perhaps boring some of you, but it's important to distinguish. So far I'm taking x and y to be gamma dot, where gamma is a geodesic for nabla. So what would that happen? What would that give you? That gives you nabla gamma dot gamma dot. So this is 0 because gamma is a geodesic for the connection. This is going to be gamma dot inner product nabla gamma dot whatever this quantity is. Okay, and here you're going to get gamma dot of gamma dot inner product z, right? Okay. So I wanted to say something precise. Yeah, okay. So, right. So maybe it would have been best if I could have written, but if x is equal to y is equal to gamma prime and gamma is a geodesic, this term drops off. So now you have gamma dot, nabla gamma dot z, gamma dot inner product gamma dot with z. Okay. So now you assume that this z is a parallel vector field with respect to gamma dot, okay, which means it satisfies this equation. So what would that give you? That would basically say that this is 0, correct? So the right hand side is 0. So then you are getting the same thing, that you are getting d by dt of gamma dot with z is 0. So what does that tell you? That basically tells you now you have a geodesic with respect to the connection, and you start off with the vector z0 at gamma 0. And the parallel transport tells you that the parallel transport is a way of transporting this vector z0 along the curve gamma such that you at time t you get the vector zt. This is a tangent vector at gamma t, but this tangent vector has this property that if you dot product zt with gamma prime t, this is a constant. That's what you're getting, right? You're getting d by dt of gamma prime t with zt. That's 0 because the right hand side became 0. That says that if you are parallel transporting a vector along a geodesic of the connection, then the parallel transported vector, the inner product with the velocity is preserved along the curve. So that is what, so in essence, if you didn't like parallel transport, but if you like metric compatibility, then you're saying that this is what a parallel transport should do along geodesics of the connection. So whatever the velocity fields are, if you start with a random sort of stick like vector z0, which is pointing out, and imagine the geodesic is some sort of a spiral or a straight line curve, and then the stick will actually move along the curve because you're parallel transporting them. And because it's metric compatible, the stick has to move in such a way that the dot product of zt along with gamma prime t is constant. So if gamma prime t increases in length, I mean, which it cannot now, it has to be the same length, which means the length of zt is fixed and the angle between zt and gamma prime t is also fixed. So that does not mean that zt is rigid. Zt can still move around. So you can imagine that your gamma is like a straight line and your z is like a perpendicular stick, and it has to stay perpendicular to the velocity of a straight line, but the stick could still rotate, right? So, I mean, at this point, that's the best explanation that I can give you. I mean,
And sir, can you repeat what you said about the length of z? The length of z might change, right? But the angle between gamma dot and z will
yeah,
remain
yeah.
constant.
So in this case, because the length of gamma is fixed, because gamma is a geodesic to the connection, what you get is that length of zt times cosine of the angle. This is a constant.
Hmm.
Yes. So in general, right. So the length of z can change, and the length of I mean gamma can change, and the angle between them can change as well. But it's this dot product which is fixed.
Hmm.
Yeah. So that's
So,
what.
effectively, both length and angle can change, but it's the dot product which is fixed. So,
Yes.
as you give an example,
Yeah.
the
So that,
if,
yes.
so if gamma is a straight line and z is a perpendicular to it, so z will remain. So the length of z might change, but then z will still remain perpendicular because cos of 90 is 0. But had it been any other angle apart from 90 degrees, then the length and angle both would have changed simultaneously, so that the inner product with gamma dot remains same.
No, no, yeah, but that's a very specific case. See, that's a. I mean, I intentionally gave you a slightly misleading example because I haven't specified where this is happening. So, if you imagine this is happening in Rn, then you have to specify what is the metric for which the straight line is a geodesic for that connection, right? So the point is, if you take the standard Levi-Civita connection on Rn, then parallel transport is the obvious transport. There's no rotation going on whatsoever, so nothing changes. Right? So when I say imagine gamma is a straight line, I'm pretending that there's a space, there's a connection where the straight line is a geodesic of that connection. Right? But
Yes.
I said this example because we will talk about this example quite a bit in the next lecture, and this is a very important example into Eli Cartan. But the point, the upshot of this whole thing is what you get is that the dot product of y and z is constant along the vector field x, which is gamma dot, if y and z are defined to be parallelly transported vector fields, simply by how these are defined. So you have to move them along the curve such that the dot product is preserved.
Okay.
So, okay. Any other questions? Okay, so yeah, so this is one way of thinking about it. So it's just saying that the metric is somehow preserved along curves, along gamma prime. That's the way to think about it, because the metric is determined by lengths and angles between them, right? Okay, so all right. So there is an alternate way to think about metric compatibility, and this is what we'll get to. So this is again, so first we'll give you some heuristics and then we'll formalize the heuristics, okay? So what is the heuristic? So the heuristic says that you're differentiating this quantity along x, okay? Fine, to differentiate that, so how many terms do you expect? Well, if you think about it, you have y, that's a variable, you have z, that's another variable, but secretly there's a third variable, right? So can anyone say what that third variable is?
T.
Correct. So it's this inner product is happening with respect to a Riemannian metric, which is also varying. So there's a third variable which is g. So naively or otherwise, actually this is not naive. If you're differentiating some quantity of three variables with respect to x, and everywhere we're going to see that Leibniz rule is what we're going to sort of allow ourselves to be dictated by, you expect three terms, right? So it has three components essentially, y, z, and the metric g. One expects three terms. So the three terms should be, first of all, it should be that the covariant derivative happens to y, and then the metric and the z are the same. So that is nabla x, y, z, or the covariant derivative happens to z, y and the metric are the same, or you have to somehow differentiate the metric g and y and z are the same. That's what you should get ideally, right? As three terms. So remember there is this, let me go back. So these two terms are automatically there. And if you differentiate this, you expect a third term, which is going to be something like y, then nabla of g, where g is the metric in the direction of x, and then z. But that is not there. So saying that this identity holds should be somehow, at least heuristically equivalent to saying that this mysterious quantity which is not there and you do not know what it is, should be zero, right? So let me go back, or let me come back to where we were. So the missing term should be of this form, right? So this is just heuristics, but you agree that there should be three terms. If you have seen enough things in calculus, this is how things should be for all choices of x, y, and z. So since this is true for all vector fields y and z, ideally this quantity should be zero, but this is for all x, and usually we would write this as saying nabla of g is zero. Okay? But what is nabla of g? Nabla only takes in a vector field as a subscript, and then it's an input. So it basically has two inputs, two vector fields, and the output is a vector field. So what is nabla of g? G is not a vector field. So there's a way to formalize this process, and that's what we're planning to do in the next few slides. Okay. So is the heuristic more or less meaningful? Okay. Okay. So to make sense of this reasoning, we need to be able to differentiate G. So let's go back and revise what G is. Okay. So first of all, G is for every point P, it's a bilinear map, right? From TPM, tensor TPM to R. It's smoothly indexed by the point P, so that's why it's a smooth map. But individually, GP is an inner product, so it's a symmetric map. It's positive definite, and it's invertible, right? So okay. Anyway, so you can think of GP instead of a map from V tensor V to R. You can think of it as an element in the dual, right? And a map from V tensor V to R is nothing but an element of V tensor V, the dual of that. But these are finite dimensional vector spaces. So V tensor V dual is nothing but V dual tensor V dual, right? All right. Okay. So this is an exercise, and I put a star here. If you do not want to do it, that's fine by me. But for those of you who want to understand this better and perhaps learn more geometry later on, this is something you should do. So you have to show that Tm tensor Tm is a vector bundle over M, and G defines a smooth section of T star M tensor T star M. So I'll not explain this any further. For those of you who will try to do this, perhaps you will read up the relevant things and try this later on, and then you can ask me. For those who do not plan to do this, you can skip this thing entirely, because I don't want to go into a discussion of how you can talk about tensor products of vector bundles and what vector bundle is to begin with. So that's that. Okay? But the point here is that a Riemannian metric can be thought of as a smooth section of some bundle. Okay? Although this is not a very practical way of defining a Riemannian metric, because then you wouldn't be able to do all these various local computations. But it takes care of smoothness in one go. That's the advantage of this definition. Okay, so anyway, but some of these things some of you, or at least most of you, I think, have seen and heard. So a metric in our sense is going to be what? For every P point in the manifold, you're getting an element here. So this is basically a symmetric 0-2 tensor. Remember, if there was a wedge here, instead of a tensor, that would be a 2 form, correct? Because an element of TP star M, as P varies, is a 1 form. A 1 form is nothing but a section of the cotangent bundle. So if there's a wedge here, it would have been a 2 form, but because it's a tensor, it's a general tensor, but because the map is symmetric, this is actually symmetric in the indices here. So it's a symmetric 0-2 tensor, but it's a 0-2 tensor because you have 2 copies of T star and no copies of Tm. Okay, so that's what a 0-2 tensor is. Now, what about K forms? These are things you have seen. So differential K forms are skew symmetric 0K tensors. Remember, 0K means that they are smooth sections of T star M, wedge T star M, wedge T star M. So they're skew symmetric, and there's no tangent component. There's only cotangent components. Okay? And vector fields are 1-0 tensors because vector fields are sections of Tm. So these are basically at every point P, this is an element of TPM. There's no contribution from T star. So similarly, multi-vector fields are L0 tensors. There's no contribution from the cotangent part. Okay. So this is just a basic nomenclature of tensors, and I'm just recalling this for you. So the point that we are making here is that we want to extend this connection and how differentiating an object along a vector field using this connection to all PQ forms. Okay, so or all PQ tensors rather. So all PQ tensors mean these are basically smooth sections of these kind of objects. So these are again going to be bundles or analogous to TM, T star M, TM tensor, T star M. These are again going to be those kind of things. So if your Q was 0 and P was 1, these would simply be vector fields. And we know how the covariant derivative nabla acts on vector fields. If P was say 2 and this was 0, then you have to extend it to sections of Tm, tensor sections of Tm, and so on and so forth. Okay, so that would be the aim, because at the end we want to apply this connection to P equal to 0 and Q equal to 2, because that's what our Riemannian metric is. Okay, if I know how to covariantly differentiate all PQ tensors, I know how to covariantly differentiate a Riemannian metric, and then I can make sense of the equation nabla of G is 0. So does that structure make sense? Okay. So for those of you who are seeing this for the first time, at least formally, just make it a point to go back, read this on your own, and see if this makes sense. So you don't have to spend too much time on why this is a vector bundle. Just take it from me that it is a bundle, meaning that it is a space which maps to M surjectively, and locally this looks like M cross Rn. Like Tm looks like M cross Rn, T star M looks like M cross Rn. This looks like M cross Rk for some K. So it has those local structures. Okay. So here is how to do it. So step 1, you extend first a given connection to 0-1 tensors. So remind yourselves that 0-1 tensor is nothing but a differential 1 form. So we know how nabla acts on a vector field, that's a 1-0 tensor. We want to determine how nabla acts on a 0-1 tensor, which is a differential. So you find a 1 form alpha and So the x is going to be the direction in which nabla acts. So this x is always there as a subscript. So given a one form alpha and a vector field y, you define the covariant derivative of the one form alpha along the vector field x to be defined by this formula. Excuse me. So okay, so I'm writing it in this form because this is much more easier to remember and recall rather than writing it in the other form that I write this on the other side. So this should remind you of some sort of a Leibniz rule. Remember, alpha is a one form. So alpha acting on a vector field is a smooth function. X acting on a smooth function is whatever it is. And then I'm saying if Leibniz rule were to be true, then you'd somehow be able to differentiate alpha along x, and that should give you a one form, right? Because this is just the differentiation direction. The one form, the output is going to be a one form. So this one form acts on y, that's a function. On the other hand, alpha stays fixed, and now you have to apply the derivative of y along x. So that is nabla xy. So this is a vector field. Alpha acts on a vector field is a function. So this is
Sir, when you are saying a 0, 1, it means covariant in rank 0 and contravariant in rank 0 and covariant in rank 1. Is that what you mean?
yes. Okay. So see, as I mean, what I mean is something very specific. When I say 0, 1 tensor, a 0, 1 tensor is something which is going to be a section. So when I say a PQ tensor is nothing but in our context a section of this quantity. Okay. So
So I mean, when in physics, when we talk about a P comma Q tensor, we generally mean a tensor which is a contravariant in rank P and then covariant in rank Q.
yes, that's true. But you see, when you're dealing with these tangent things, these things are already covariant, right? Because if you have a map f from m to n, then you get a map from tm to tn. And when you look at t star m is contravariant because you can always pull back. So when you have a map from m to m, you get a map from t star m. So it is in that sense that it's covariant, contravariant. But in this particular case, this is a very specific thing. So I mean, it is agreeing with what you're saying because the p part corresponds to things in tm, and the q thing correspond to things in t star m. And one is covariant, the other one is contravariant. But in our context, it's even concrete because I'm saying a PQ tensor is nothing but a section of this, which means for every point X, sorry, unfortunate that there's a P here. For every point in the manifold, PQ tensor is going to assign an element here, tensor an element here. So if I put P to be 0 and Q to be 1, what is this object? This is nothing but, this is just R because this is Tm tensor 0, that is just the scalar field R. R tensor anything is just whatever is left here, but this is T star M tensor 1, which is T star M, right? So this simply become differential one forms. And similarly, if I talk about 0,2 tensors, 0,2 tensor is not going to be a differential two form because I'm not specifying skew symmetry. It's just going to be something like dx1 tensor dx2. Okay, does that clarify your doubt?
Sir, can you just explain a bit why did you say like why is T star M covariant and TM contravariant?
No. So the usual way you say covariant contravariant is this. I mean, for mathematicians, this is how it comes about. If you have a map f from m to n, then you look at these various induced maps that you get from f. So f automatically, let's say, gives you a map df, right? The pointwise linearization. But what is the map df? Which direction does it go? It goes from tm to tn. So it does not reverse the direction, right? So in math, when you say covariant, contravariant, this is, or even as a functor, this is what we mean. So when you have a map from m to n, the linearization df is a map from the tangent bundle tm to tm. So the direction is still the same as f. So that's a covariant thing. Whereas if you look at t star m, that one reverses direction. So if you have a map from f from m to n, usually when you pull back, you wouldn't have a map from T star M to T star. I mean, you don't have a map from T star M to T star N in any case. You only have a map from T star N to a certain pullback bundle. But the arrow reverses. It goes from something associated to N to something associated to M in the case of the cotangent bundle. So that is what we mean by contravariant. That it's F is like an assignment, and then you look at various associated maps to F, and whether the arrows reverses or not is when you call those things covariant or contravariant. So TM is something that if F is from M to M, TM and TM are associated by the same direction. Okay? And the opposite happens for T star M, but you have to take the appropriate pullback and so on. So to me, that would be how I would call covariant and contravariant. But as I said, the best way to think of this in geometry is simply the fact that this is a section of this bundle. Whatever this thing is, that's immaterial. Whether it's covariant, contravariant, this contains all sorts of things, symmetric, antisymmetric, all sorts of things. So an element, a section of this bundle is really how I would want to think about this at an abstract level. These could be all sorts of other things as well. This is just a very specific case. Okay. So, and we are in the specific case when P is 0 and Q is 1, but that simply becomes T star M, because this becomes R, and R tensor anything is just this thing, and this is T star M tensor 1, but B tensor 1 is just B, so that's T star M. Okay. So our first time is to extend it to differential one forms. Are there other questions? Okay, so this is what the Leibniz rule tells us, that you better define it this way, which means I can define nabla of alpha along x to be this quantity, and I move this term to the other side. But I'm writing it this way so that it's easier to recall. Okay. All right. So this is an exercise which I would want everybody to go back and try. So we have defined something. So, right, so we have defined our nabla x y to be what? This quantity minus this. So one has to go back and check that this is actually a connection, right? So what would it mean to say that this is a connection? Well, remember, earlier we had sections of TM, sections of TM, sections of TM, because everything was TM. Now we have sections of TM. Well, this quantity will always remain TM, because this is this x, where the x is coming from, the direction. This is the new bundle that you have. Instead of the tangent bundle, you have the cotangent bundle. So the input is a one form, the output is also a one form. So how do you check that this is a connection? Well, you have to show that it's C infinity M linear in X, and it satisfies the Leibniz rule in alpha, correct? Which means if I scale f alpha by a function f, then nabla f alpha along x should be x of f into alpha plus f into nabla x alpha, the usual thing. Okay? So you have to check these two conditions. And this is an exercise because I think it will be good to get your good to get your brains working and hands dirty to know what exactly works and what doesn't. So you could have defined this formula even otherwise, by accident, trial and error, but the point is this is really being dictated by the Leibniz rule, and one checks that this is a connection. Okay? So that's good. So that tells me that the nabla can also be defined for the cotangent things. Okay. Any questions on this exercise? So we just have to check a few things, but hopefully the motivation is clear of why we defined it this way. Okay. All right. So that's step one. Okay. So how do we calculate this nabla locally? So remember, we always want to work locally and calculate this, because we want to say that I want to put x equal to del by del I. And what is the one form? Remember, a one form is locally given by fi dxi. So f1 dx1 plus f2 dx2 up to dot 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 fn dxn. So this is what a one form looks like locally. So to determine this nabla locally, it suffices to calculate nabla del by del xi dxj as a one form, correct? This is what we have been doing even for the other connections. You simply try to figure out the Christoffel symbols, and then that determines the connection. That's what we're planning to do. So we work with the one forms dxi's, which form a basis of TPM for all P in the local chart U. And this is dual to the basis del by del xi. All right, so let's do that. So you see, you calculate the covariant derivative of the one form dxj with respect to the vector field del by del xi. So how do you calculate this one form? Well, you calculate this one form by evaluating this on a dual basis. So evaluate this on del by del xk. By the formula, this is nothing but del by del xi of this quantity minus dxj of this quantity, right? And it is this because you will be doing del nabla del I del xk, right? Remember, this is this form, right? This will appear as the last term. This is dxj and this is nabla del by del I del by del xk. So that's what happens, right? So it's a sum, Einstein summation convention. This is ik because this is nabla del by del I del by del k, and this dxj acts on this. So what happens to the first term? Well, this is simply going to be delta jk. Remember, this is a dual basis. So this is delta jk. And what about here? Well, this is dxj acting on a function times this, but the function pulls out. So this is dxj acting on del L, right? But dxj acting on del L is also going to be delta jl because it's dual basis. So this is what you're going to get, correct? This is del by del I of the delta function or the Dirac delta, and this is the Christoffel symbols, but acting on delta jl. Okay? And I've just switched from L to J here. Some of you might have noticed that. The reason being that this is dxj on del. So the point is the only time this is non-zero is on L is equal to J. So might as well put J here and then forget about this. Okay. So the point is this should be L, but then because this is only non-zero and J is equal to L, this term drops off. You simply have this left. What about this? Well, del by del I of delta is 0 anyway, because delta jk is a constant. It's either 1 or 0. So this is gone. So what we obtain is this, correct? So this one form acting on del by del xk is just this number. And this is true for all k, which means this as a one form looks like minus del upper j lower ik dxk. I'll just pause here for a moment. I'll let you run through this thing. See if you have any questions, and then I'll continue. All right. So any comments or questions? You should notice the difference of how things appear. So this is not like in the old Christoffel symbol. If this was del by del xi, del by del xj, this would have been del gamma to the k ij, and there's no minus sign. Okay. Whereas here, there is a difference, right? The difference is that there's a minus sign. The k sort of appears down below. I appears down below, which is what it should be, but j appears up. So there's some change in the positioning and signs. So this is, so if you want to think about this, the Christoffel symbols of the connection for T star are related to the Christoffel symbols of the original connection on Tm, but there's this change that the j and the k switches places, and then you have a minus sign. All right. Okay. But nonetheless, so it basically gives you a very concrete recipe of constructing this connection. You declare the connection to be this, and then you extend everything by C infinity here, Leibniz root here. So these are the Christoffel symbols for the connection on the cotangent bundle. So although we'll not see much of this from an exam point of view, but I thought this is worth seeing at least once in a Riemannian geometry course, because this is something that you will have to sort of live with if you ever do something in Riemannian geometry or differential geometry. The fact that the connection extends to all tensors is a very key fact. Okay. All right. So this takes care of step one. So step one says, how can we extend this to one forms? Well, this is how we do it. This is a concrete procedure. The abstract procedure is you define it using Leibniz root. So what about other tensors? What about 0, 2 tensors? What about 2, 0 tensors? Well, it's Leibniz rule back again. So the aim is to extend to all PQ tensors. I'll just do one for you because this whole process is not so important rather than the fact that it can be done. So you have to extend to all P0 tensors. P0 tensors, remember, simply means multi-vector field. So this is a section of TM tensor, TM tensor, TM. So at every point P, you basically have every point X, you have a P tuple of vectors. Okay? And similarly, 0P tensors, these are sections of T star M, tensor T star M, P copies. Okay? So this is how you do it. So suppose Y1, Y2, Yp, these are vector fields. You define nabla X of this quantity to be nabla X of Y1, the rest stay the same. And you simply just apply Leibniz rule at each slot. So the last term is going to be Y1 up to Yp minus 1, tensor nabla X of Yp. And this is now again going to be a multi-vector field, right? Just Leibniz rule. So once you know how to do it for vector fields, which is by definition, and once you know how to do it for forms, which is by Leibniz rule, you know how to do it for every other PQ forms by Leibniz rule, because every other PQ tensor, rather. Okay? So this is it. So even if these were one forms, the same formula applies. You'll be doing nabla X alpha 1, then the whole thing tensor alpha 2 up to alpha P, all the way up to alpha 1 tensor alpha P minus 1 tensor nabla X of alpha P. And that is again going to be a 0P tensor. Okay. So any questions before I move on? So we extend everything by Leibniz rule simply by imposing it. Okay. Okay, so the same method applies to PQ tensors, and I'll not go further into the details, but I'll remind you that you might say, okay, what about 0,0 tensor? Well, 0,0 tensor is nothing but the sections to the trivial bundle, for those of you who know bundle. So this is basically nothing but a smooth function. So how does nabla X act on a smooth function? Well, it acts by how the usual covariant derivative should act. It's just X acting on F. But this is nothing but df acting on the vector field X. Right? It's just the directional derivative of F along the vector field X. So this is how nabla X acts on F for all smooth functions. So now that we have defined what nabla does to a PQ tensor, we are in shape to talk about what it does to a 0,2 tensor. And remember, the Riemannian metric was a very specific 0,2 tensor. It was a symmetric 0,2 tensor. So let's recall what this Riemannian metric does. In local coordinates, a Riemannian metric looks like a sum. And again, if I were using the Einstein summation convention, I would have simply skipped this sum because the J appears here and up here. The K appears here and up here. So this is GJK dxj tensor dxk, and GJK is nothing but the inner product of del by del xj with del by del xk, right? So this is a 0,2 tensor. Okay, this is not a wedge. It is like this, and because GJK is GKJ, this is a symmetric 0,2 tensor. All right. Okay. So if you wanted to now talk about nabla G, well, you better talk about nabla del IG. What is nabla del IG? Well, nabla del IG, remember, is going to be, you have to take this as a 0,2 tensor and you have to differentiate this with respect to del by del I. That means you first differentiate the function with respect to del by del I. But by this condition, this is simply the directional derivative of the function GJK in the direction d by dxi. So that's the first term. Right? You're using Leibniz rule because now you know what to do. So this is the first term. These two stay the same. What about the next term? Well, the next term is this stays the same. You apply the covariant derivative on this term. So that's this. Right? The last term stays the same. What is the third term? Well, it's the same thing. The first two stay the same, and then it's a covariant derivative nabla d by di, del by del I, acting on dxk. Right? So if you have followed this up to this point, let's simplify what we get. So the first term is just what it is, right? It's the ith derivative, the derivative of gjk in the ith direction, along with dxj tensor dxk. What about the next one? Well, the next one, remember from our old formula, when I have nabla del by del I, with dxj. This is a minus, the j goes up and the L comes down, and this is what we obtain. The Christopher symbols come with the minus sign and the switch. And again, this is a sum over j, it's a sum over k. I'm not writing the sum, and this is a sum over j, sum over k, and sum over L, because this contributes sum. Okay, so this is a triple sum over here. What about the next term? Well, the next term is the same thing. You have del I, del k. So I stays below, k goes up, and the L appears here. Right? So is this okay so far? So this is a triple sum, this is a triple sum, this is a double sum, because originally this was a double sum. Just keep that in mind. So what do we get? Well, if you simplify and then you write everything as a double sum, you pull the dxj, dxk out. This is actually a sum over j and k. This is the first term. This is the second term. This is the third term. Okay. And I'm just relabeled some of the indices, but this is a sum itself over L. This is also a sum itself over L. Right? So we are almost there. So if you want to claim that this quantity must be 0 for all I, that means what? That means this quantity is 0. But remember, dxj tensor dxk, this forms a basis of T star m tensor T star m. The sections of T star m tensor T star m, because this has the right dimension. So this is a sum over j and k. So this being 0 means that this coefficient has to be 0 for all I, because this has to be true for all I. So this coefficient has to be 0 for all I, j, and k. Correct? So I'll pause here for a minute, and you can just go through the computations and see if there are sign mistakes or how the indices change. And then I'll move on to the next slide. But for those of you who might have observed this already, you should remind yourselves that this is something we had seen in one of the first few slides when we discussed metric compatibility in local coordinates. So this should remind you of something and ring a bell. This is not something we're seeing for the first time today. And I'll point that out in the next slide by maybe going back. But are there any questions so far? Okay. So we want this quantity to be 0 for all I and j and k. If we want nabla of g to be 0, that means equivalently nabla of g with respect to del I is 0. Okay. So yeah, so as nabla g is 0, if and only if this is 0 for all I, and that's because in this coordinate it's C infinity m linear. So if I put any vector field locally, I can express it as summation fi d by dxi. So this being 0 is equivalent to this quantity being 0. So we have a criteria, right? So the criteria is that this quantity must be 0 for all I, j, and k. And remember, this is a sum over L, and this is a sum over L. So the exercise for you now is to show that this condition is true if and only if nabla is metric compatible. And I'll give you a moment, and then I'll go back to one of the first slides that we talked about. So this is the condition that we obtain just by defining nabla on generalized tensors and then declaring nabla g to be 0. So why is this familiar? Well, if you go back a long way, just bear with me for a minute. It will take me a while to go back. So you see that this equals this plus this. So this was what we had using metric compatibility in local coordinates. And the job that you have right now is to basically do a bookkeeping thing, that compare what we get from this equation in the second slide to whatever we have at the current slide, and then it's a matter of checking that they're one and the same, right? So it's the same thing. We're not getting anything new, but the approach is slightly different, and we're actually obtaining something more in the process. That we can talk about the covariant derivative of PQ tensors. Okay? Yeah, so we're back here. Okay? So this is the upshot, that a connection is called metric compatible if and only if nabla of G is 0. And this is just the same identity that we had before. And this is not too surprising in hindsight, because this is saying that the covariant derivative of the metric is 0 along any direction x. But that means that the metric is preserved under parallel transport. But that is precisely what we deduced at the very first setting, right? We said that the metric is preserved along parallel transport. So they're both defining the same. Metric compatibility means that nabla of G is 0. It means this equation is 0. It also means that the metric must be preserved along parallel transport. They're one and the same. Okay. So sometimes you might see this as the defining definition, but this is slightly advanced, because to define this and make sense of this, you have to talk about how to extend nabla to PQ tensors, and that takes a little work to get there. But now that you have done it, hopefully you have seen the two usual ways one talks about metric compatibility. Okay. So, are there any questions so far? Okay, so yeah, so that's essentially it. There was a little bit regarding torsion, but I didn't want to start it today, because I'll probably start afresh with torsion free and torsion in the next class. And I plan to talk about Elie Cartan's seminal work and how he introduced the notion of torsion, primarily inspired from physics. So yeah, are there any questions? Sorry, or anything that you want me to go back to, maybe just clear out? I'll just give you a couple of minutes, and then maybe we'll wrap it up. Excuse me. Okay. All right. So if there are no questions, fine. Let's like finish up today. I'll send out the slides for next Monday's talk, maybe in a day or two.